So I'm a bit curious. Have you obtained a copy of the textbook? I say obtained. I'm asking because just for unrelated. Any of you from ECS 那个电子院学士班? Okay, so we are going to remodel your 系学会办公室, your Office of Student Association. I'm currently the chair, in case you don't know yet. So just Yihui, Miss Zhang Jian Yihui, Miss Yihui discussed with me that we want to put a bookshelf in the office so that you can pass on your textbook to younger students, to the younger generation. So I really like that idea. Yeah, I mean, if anybody has a textbook that you think you're not going to use anymore in your life, you figure out this piece is not helpful for your life, but you have the textbook, please pass it on to 系学会, so that newer students, your 学弟妹, younger students can use them, right? But I like the idea. I highly recommend you to, if you're interested, to find a copy of the textbook. Okay. In the old time, we asked, student bandai, ask somebody to help buying textbook. Do you still do that? Do you still buy the textbook together so you get discount? 可以打折? Probably not. I haven't seen that for a long time. Yeah. But anyway, one reason I mentioned this is back to this next lecture is going to be about some selected properties, 选择性的. I'm going to choose a few properties of the DTFT, Discrete-time Fourier transform, the DTFT. So we are going to go over, but I choose this. Later we'll see that I'm choosing some properties to report to you, so that those are the properties that I found that are quite useful, often used in this for DSP. Okay, so that's why I choose to show to you a few properties, to mention to you. But for a more complete coverage of the topic, please check the textbook. Okay, 我要完整化. If you want to just know thoroughly every possible property of the DTFT, please refer to the textbook. Here we are only going to see a few properties. Okay, but before we see the properties, of course, we see the definition first. So here let's go over this slowly. Here is the definition. Okay? The definition goes that we begin with a sequence. Now things are already after C to D conversion, already in discrete time. So we have a sequence, x bracket n being integers. Okay? So we have a sequence of numbers, and then we can define its DTFT as this using this equation. Okay? Using this equation. So in this equation, there's a summation. X, your signal goes here, and we multiply your signal with e j omega n. There's a minus sign. Okay? And we sum. We calculate infinite sum. And the result becomes a function of the beware of the notation small omega. Okay, previously, we had big omega, right? But here now in this definition, because n is integer, we use small omega, lowercase small omega, to denote the frequency variable. The result is a function of small omega. Okay, so far so good. So that's the definition. And the result is still we just stick to the same convention, small x in time, big X in frequency. The result is in the frequency domain. We go from time to frequency. And this is the definition of DTFT. Okay? Yeah. So the result of a function of frequency small omega. So now I invite you to first think about the unit of omega. Okay, the unit of small omega. What's the unit of small omega? You can say that small omega does not have a unit. That's fine. There's no physical dimension being hertz or anything. Okay, But if you really ask me, I recommend that we can regard the unit as radian per sample. Radian per sample, because omega really is some kind of frequency. Some kind of frequency. It tells us how much of phase is accumulated when time is advanced by one sample. Let me repeat that. Okay. Omega, it shows up right here, e to the, it's not important, minus j or plus j, but just minus j omega n. J omega n equals to cosine omega n minus j sine omega n, right? So it shows up inside cosine or sine. Omega is right here. So it has a meaning. The meaning is when we go ask the question, when time is advanced by one sample, then the phase right here, omega n, the phase, this is time. When time advances by one sample, then the phase advances by how much? That's what omega means. The phase is advanced from omega n to omega times n plus 1. So delta omega, if you will, the phase advancement, the phase progress, the phase advancement, phase changes, the phase changes by how much? By, well, that's stupid. Delta phase, not delta omega. I'm sorry. Yeah. If we denote phase by theta, okay, phase is theta, time is, yeah, then delta theta equals to omega times 1. So therefore, omega has a unit. It tells us how much phase it is advanced when time is advanced by 1. So therefore, I recommend we can think of the unit of omega as radian per sample. Radian per sample. How much of phase is advanced when you can really talk about this. How much of a phase is advanced when we have a sinusoid, a sine function, and then we ask how much phase is advanced when time advances by one sample. Okay, omega does have a unit. Okay, it's a frequency. Basically, omega is a frequency. So now, the next question we should agree with is that I invite you really still x of n. In this course, think of x of n not simply as a sequence of numbers, but as the outcome of sampling. The outcome of sampling, always we think of our signal, discrete time signal, as the outcome of sampling a continuous time signal. Okay? Still that we do this. Okay? That's the way we think about x bracket n. We still think about x bracket n in that it's a result of sampling a continuous time signal. There should be a C here, but I'm being sloppy. So notation 比较随便一点, being sloppy. Okay? So agree with me, but the idea is that think of x of n as a result of sampling a continuous time signal. Then when we do sampling, we need to specify the sampling period, right? So now the next thing I want to bring up is that there is a convenient way to convert between small and big omega. To convert between small and big omega. Okay? Small and big omega. So the idea really is when we say this is in n is 0, 1, 2, 3, and so on. That's n. But the same plot, you can think of this as a result of sampling a continuous time signal. Now, then that's a continuous time variable t, right? So here, really in yellow, we have 0, 1t, 2t, 3t here, okay? With the sampling period fs being 1 over t, okay? So now, quickly, you can really check to convert between small omega and big omega. There is this relation. Small omega tells us how much phase is accumulated by one sample, right? Big omega, what does it tell us? Big omega tells us how much phase is accumulated by 1 second. It's 2 pi times frequency. That's big omega, right? So big omega tells us how much phase is accumulated by 1 second, while small omega tells us how much phase is accumulated by 1 sample. That's a relation, okay? So how many samples do we have in 1 second? How many samples do we have in 1 second? That's Fs, right? Therefore, big omega should be Fs times small omega, or small omega is T times big omega. Yeah. So that's a way quickly, okay? That's the way I make my conversion quickly in my mind. Whenever I see small omega, I would ask, then tell me your sampling rate. Tell me your sampling period. So I can be sure what small omega corresponds back in the real frequency in hertz. Yeah, this is a bit quick, but let's look at let's do an exercise. Okay, let's do an exercise. What does omega equals to pi divided by 6 represent? So then what should we ask in response? Show me your sampling rate. Okay. All right, so then I say, okay, my sampling rate is 48 kilohertz. Okay, 48 kilohertz being the sampling rate right here, 1 over t. We have 48,000, 48,000. We have 48,000 samples every second, in every second. And then we are interested in looking at omega equals to pi divided by 6. Then what does that frequency correspond? What's the corresponding frequency in hertz? That's an exercise. Okay, that's an exercise. Yeah, maybe I can stop for 1 minute. So just think about, make a contemplation, and then I will work out. Okay, what does pi divided by 6 correspond when the sampling rate is 48 kilohertz? Do a simple calculation. Okay, now we have 60 seconds from now. Yeah, this is important. This is important. Yeah, just to cover the basic first. Yeah, I really want you to be able to make the conversion. 这个切换switching between small and big omega is quite important at the beginning. You'll get used to it. Using this relation, small omega, big omega, there's a factor of sampling period or sampling rate. 好, 30 more seconds, and then we'll check our answer. Okay, yeah, almost there. 10 more seconds. Okay, so then we work on the answer. Okay, all right, so just simply to check your answer, I say big omega is sampling frequency times small omega, right? Yeah. So sampling frequency is 48 kilohertz. Now times small omega is pi divided by 6. So big omega should be 8,000 pi. Okay, 8,000 pi in radian per second. That's a corresponding frequency, the frequency that which corresponds to pi divided by 6 when sampling rate is given as such. But now this is equal to 2 pi times the actual frequency in hertz, right? So therefore, the corresponding frequency is 8,000 pi divided by 2 pi, which equals to 4,000 or 4 kilohertz. Okay, so that's the answer. That's the answer. Okay. So yeah, just do it repeatedly and you'll get it. Okay. So that's kind of the convention. 这个习惯 is a habit. Is how we handle the conversion in this textbook. In this textbook, small omega is for discrete time, big omega for continuous time. Both are frequency, and you do need to use this conversion. Okay? So please make sure that you are familiar with that. Yeah, either for math or for computer programming. Okay? For programming, you need to make sure you understand this. Okay? Yeah. So a quick way is now still, even for this easy result, is contemplate. So in my mind, I always think of pi. Pi corresponds to the Nyquist rate. That's the easiest way to understand. Pi corresponds to half of the sampling period. So pi represents 24 kilohertz in this example. That's the way I remember it. Okay, just to share with you, if pi is 24, then pi divided by 6 is 4 kilohertz. Okay, so that's the way I do my quick calculation. But anyway, this is easy, but just make sure that everything makes sense, right? Yeah, just make sure everything makes sense. But otherwise, this definition goes from time domain to the frequency domain. And next, I'm going to talk about inverse transform. Let's talk about the inverse transform, right? Maybe we can erase this part. So here is a result we can check. Okay, so just recall that the forward transform from time to frequency is defined as summation x of n, and we make a projection by doing inner product. Essentially, there's a minus sign right here, summation over all n. Okay, now it turns out that we want to check. We can go from frequency domain back to a time domain. Okay, by doing this calculation. 2 pi integral from minus pi to pi, and the spectrum, the DTFT, times E j omega, and the integral is with respect to the small omega, the frequency. And this expression takes us from frequency domain with the spectrum back to the time domain. The result will be a function of n. The result will be a function of n, right? But we want to check really, does this get us, does the equality really hold? Okay? Because if it holds, then this defines an inverse transform. It takes us from the frequency domain back to the time domain, right? So I claim that this is correct, so that we need to check. We need to check. Okay? But before we check, you can realize that everything is very similar to continuous time, the original version of Fourier transform. Okay? So here still there is the integration, right? But now the range is from minus pi to pi. Okay, we'll see that. But the idea is still take the spectrum, because the spectrum tells us how much of a signal we have at that frequency. Spectrum, right? Spectrum means frequency domain. How much of a signal do we have at that exact frequency right there? So if omega, for every frequency we have a component whose magnitude and phase is denoted by this complex number, then this is the way we put everything back together. So it makes sense. This is some people also call this a synthesis equation. Okay, so this can be regarded as a synthesis 合成的 synthesis equation. It's in the textbook. Synthesis equation. Because we start with the spectrum and then we go back to a time domain by putting everything together. It's like making sound, making signal, right? So it's also called a synthesis equation. The idea is to collect all the terms in the frequency domain, and then each term has a magnitude like that. Each term in the time domain should look like this. Then we collect everything by integration. Okay? 2 pi needs to be there, and we'll show it. Okay? Any questions so far about how to interpret going back to time domain? Okay, so it makes some sense, but we can completely check this. Okay, so now just let's check. Okay, so here we don't know for sure, but here let's just copy 1 over 2 pi here, and then what do? We need to substitute this by the definition. We not need to substitute the spectrum by its definition, right? So the way we check it is still keep the integral here, but make the substitution x equals to summation. And just to be smart, I want to rename my summation index. It's a dummy variable. Okay? xm e j omega m. Just not to confuse with the n right here, and this is important. Okay? We don't want to confuse the summation index, which is dummy. 就是叫什么 dummy 哑巴的 which is really just a summation index. And you don't want to confuse this n with that n here. That n here is a constant as far as this expression is regarded. Okay, so please be careful. Let's try to change the summation index from n to m. Okay, to avoid confusion. And this is important. But that's simply substitution. Okay, this is simply substitution. And then we copy this thing right here, e j omega n, and we integrate with respect to omega, small omega. So far, so good? Huh? What's next? Every time you see integration and summation, you can try changing the order. Okay, changing the order, assuming everybody's happy right here. Okay, nobody from math department. Okay, to stop us from doing this. Summation outside, integral inside. Let's try this. It might work. So summation outside. Now inside we have xm. Just copy everything. E to the minus j. Now we have these two terms. Now becomes both inside the integration. Okay. So here we do have combine the two terms. E to the either minus or plus. Plus probably easier. Plus j omega n minus m. And still we have the integration. Okay? Right? Changing the order. Okay? But when we change the order, we realize that this term does not depend on omega. This term does not depend on omega, so what can we do? Move it to the outside, right? So we're going to move it to the outside. Allow me to erase. Okay, we're going to move it to the outside. Move it to the outside. Xm outside. Small m. Apology for my handwriting. Now integration goes here. And we know how to do this integration. Okay. So now we're almost all set. But now here, we need to evaluate this integration. We need to evaluate this integration where both n and m are integers. M being the summation index, n being the n, okay? N being the time index, right? So now when you consider this integration, okay? When we consider this integration, we notice that it's non-zero only if n equals to m. When n both being integers, when they do not equal, then this integration equals to 0, or it vanishes, 它消失. When this integral is non-zero only if n equals to m. Can we agree on that? Yeah, because it's cosine plus j sine. Both are periodic, and n and m are integers. And this integration is with respect to omega, not nom, right? So let me just make a note that you want to note that this equation, this integration, equals to 2 pi when n is equal to m. When n equal to m, this becomes 0. We are taking the integral of 1 in this closed interval, right? So and the result is 2 pi. Okay, otherwise it's 0 when n not equals to m, right? So now we can continue. Okay, so with this result, hopefully we'll see that every term is going to vanish except for the term that when m equals to n. Okay, so this is now still we have this summation, and now the summation is multiplied by one thing that almost always vanishes. It's non-zero only when m equals to n. Maybe I should write it the other way around, just to emphasize that m being the summation index. That's probably more easy to understand. Okay, so we have an infinite summation, but most of them are almost everything is 0, except one term. Except that one term when m equals to n. And when that happens, the integral equals to 2 pi. Okay, so when that happens, when xm at m equals to n, when that happens, the result of integration is 2 pi. So therefore, indeed, 2 pi cancels 2 pi, m equals to n. The result is x of n for any n. Okay, so that's a kind of a short check of what's going on. We are given the definition of DTFT, the Fourier transform, and now we do have a suggestion of a formula which gives us the inverse transform. Now we have checked that by exchanging the what? By exchanging the order of summation integral, we can show that, we can convince ourselves that indeed for every small n, for every time index n, this expression gives us an evaluation of our sample value in the time domain. Okay. So we are running out of time. Yeah, we're running out of time. But so now with the definition of forward and inverse transform, you are ready. You're all set for homework number 1. Homework number 1 is going to be due next Monday. Okay, next Monday, 17 p.m. No, 17:00. 5 p.m. I mean 5 p.m. Next Monday. I understand that we have a long weekend, so the homework is not going to do until next Monday. Okay, please be aware of that. Otherwise, please sign up, and then just a sneak preview. We do have a few properties I want to go through before we move on. Right, they are going to be useful. But anyway, tomorrow for discussion, and see you tomorrow.